a sphere with radius 4.2 centimeter.
I have a sphere. The radius is 4.2 centimeters. 24 centimeters.
Excuse me. Has a uniform surface charge density per meter squared.
Okay, this is the density, not the charge.
That's the density? Yep, density
of 13.0 microcoulomb per square meter. And now that sphere actually has a charge. It's a positive charge. So there's a charge on the outside. We'll figure what that charge is. Remember, since it's positive, the charges want to be as far as possible. So on the outer layer of that sphere. Now, there's another charge right here. And we know the force between them, between the two charges. The force is 4.76 times 10 to the negative 2 Newton. And this spot has a charge of 1.25 microcoulomb, positive microcoulomb. So there's a charge here, positive charge, and this is a positive charge. So we know the force is going to be pushing away from each other. That's what the direction of the force.
And the question, what is the distance between them?
Well, we need to know what the charge on this one is. What is Q here? We have the density. Well, Q is going to be, notice the density tells you how many charges per square meter. So it's 13.0 microcoulomb times the area. Because this is per meter squared. That's per square. God. So if I know what the area is, I'm done. The area of a sphere, I think, is 4 pi r squared. If you Google that, you end up the area of a sphere, 4 pi r squared. I'm almost positive that. I should check it, but I'm lazy. So it's 4 pi. R is what? 0.0424 squared. 4 times pi times 0.0424 squared. The area of a sphere, surface area we're talking about, 0.02259. That means if you take a thin knife and you fillet that sphere and you lay it flat, the area of that will be that much. So Q, the charge now, is going to be 13 micro times that number so let's try that, times 13 micro. Is that 0.29 micro? 294 microcoulomb. That's the charge there. So now what is the force? We know force equals K times Q1, Q2 over the area squared. We know what the force is that was given to us, 4.7 times 10 to the negative 2. K is what? 8.99 times 10 to the 9. Q1, excuse me, is 0.294 micro. Q2, 1.25 micro over R squared. Four 4.7 times 10 to the negative 2 equals 0.0033 over R squared. 4.7 times 10 to the negative 2 R squared equals 0.0033. R squared equals 0.070. R will be the square root of that number, which is 0.265 meters or 26.5 centimeters. .265. So the key to this problem was first to get what the charge on this. They didn't give you the charge. They gave you the density, which is how many coulombs per meter squared. So if you know how many meters squared you have there, you know what the charge of that is. So once I figure what that is, and I know it's per area because this is meter squared. Square is always the unit for what? Area. Cube, the units for volume. So this is how you know this is per meter squared. That means per area. So that's number 22. Number 31. Do we know what Q is for that one? Find the direction. Q equals 2.5 microcoulomb. And the distance is 31 centimeters. Okay. It looks like we have a square. The picture doesn't look like, at least on my machine, doesn't look like a square, but it looks this what you have. You have a square. And the distance is, I don't know, 31 or 3.1. I think it's 31 centimeters. And here's what we have. We have charges. In the bottom left, we have a charge of positive 2.5 micro. There's a charge here, we'll call it Q1. Micro. Q2 is right here. We have a charge of negative 2 times that number. That's negative 5 micros. We have a charge here, we'll call it Q3. Negative 7.5 micro.
And we have a charge in the bottom right corner of
Negative, call that Q4, negative 10 micro.
all these coulombs, microcoulombs. Find the direction and magnitude of the net force exerted on Q2.
This is Q2. What is the net force on that one? Well, let's look at each one. This is Q1 to Q2. Q1 is positive, this is negative, this one is pulling on it. So it's going to be a force in this direction. We'll call it F1 on 2. Charge 1 on charge 2. 3 and 2, notice they're the same sign. It's going to be pushing on each other. There's going to be a force pushing in this direction. We'll call it F3 on 2. These guys the same direction. We have a force pushing away from it. That's F4 2.
Where it's Q2, where you have negative 5.
Yes.
Did you calculate that, or was that given on?
Well, it says negative 2 times Q. And Q is listed in the question as 2.5.
Okay.
Yeah.
So that's probably what I was doing
Yep.
wrong.
Yeah, everything was in terms of Q, and then when you go to the question, it says Q is 2.5 microcoulomb and D is 31.
I need to know what this distance is. And you can use Pythagorean theorem. Usually that distance, when you have a square, it's always the square root of 2 times that distance. Always. You can do the math using Pythagorean theorem. But that distance from here to there, it's always the square root of 2 times whatever this distance is. A squared equals A squared plus B squared equals C squared. If you do that, you end up with that value. I'm just trying to minimize the amount of work I'm going to be doing here, because this has a lot of work involved in it. So let me find each one of them. F1, 2. Remember, the equation I'm going to be using, F equals K times Q1 times Q2 over R squared for all of them. That's the equation I'm going to be using. So here we go. F1, 2 is going to be K, which is 8.99 times 10 to the 9 times Q1, which is 2.5 micro. Remember, the micro is 10 to the minus 6. This is negative 5 micro, so it's 5 micro. We don't put the minus, it's absolute value. Divided by the distance squared, 0.31 squared. (8.99 e to the 9 times 2.5 e to the negative 6 times 5 e to the negative 6 divided by 0.31 squared. And according to my calculator, this answer is 1.169 Newton. F32 equals 8.99 times 10 to the 9th times this and that. That's 5 micro, 7.5 micro over 0.31 squared. And again, for this I got 3.508 Newton. And F42 is going to be 8.99 times 10 to the 9th times 10 micro times 5 micro. That distance, let's see what that distance, the square root of 2 times 31. It's actually 43.8 centimeters. So over 0.438 squared. And for this I got 2.343 Newton. So these are my forces. Now I got to do a vector addition. So if you do your x and y axes at Q2, this is what you see. You see F42, that's this one, at square root of 2 times 31. Pythagorean theorem. You get a value in this direction of 2.343, and this angle is actually 45 degrees because it's a square. I got 1 in this direction, and that's F32, which is 3.508. And I got 1 in this direction, which is 1.169. And I got to find the net result of these forces. Did you get that answer? The 48, 43? Did you get that number?
Oh, no, I have different numbers.
Okay, but that's the square root of 2 times that number. Yeah. So now I got to do vector addition. And if you remember vector addition, you got to write the vectors, find the x and y component. Excuse me. God, I was feeling good too yesterday. Vector, I'm going to do the x and y component for each one. So I'm going to add the 3 vectors and find the result. So the first column is going to be the vector. We're going to write the vector here. This is going to be the x component, which is r times cosine theta. And this is the y component. This is only correct if you take the angle with respect to this line, to the positive x-axis. Then the x is r cosine and y is always r sine. That's why when we write the vector, we write them in reference or with respect to the positive x-axis. So the first vector, I'll use the 2.343. And the angle is what? What's that angle? You got to measure it from here. So 90 plus the 45, which is what? 135. The second vector, 3.508. And the angle with respect to this is what? 180. And the third angle, the third vector is 1.169. And the angle with respect to this, you can write negative 90 degrees or plus 270. Your answer will not change. And let's find the x and y component for each one of them. This is 2.343 cosine 135 negative 2.334. The y value, 2.343 sine of 135. The answer to that, positive 2.334. This one, 3.508 cosine 180. The answer, negative 3.508. The y value, 3.508 sine 180 degrees. The answer is 0. The x component for this, 1.169 cosine 270 degrees. Answer is 0. And this 1.169 sine 270, and the answer is negative 1.169. So we took each vector, broke it down to x and y components. So now let me add all the x component. That's called r sub x, the result in the x direction and the result in the y direction. In the x direction, let's add the two numbers that we have, 2.334 plus 3.508, both negative. So it's a negative 5.842. Who had a breakfast this morning? Smells good.
It's me.
Oh, smells good. R sub y, like. What is r sub y? It's 2.334 minus 1.169. It's positive 1.165. So if you graph that, you know which quadrant are you in now. It looks like quadrant 2. Why? Because x is negative, y is positive. It says to go to that, you're going to travel in the x direction. To the left, it's negative. You're going to travel in the x direction, negative 5.842. Then you're going to go up, positive 1.169. 6599. And this is what you're trying to find. What is r and what's theta? So I'm trying to find what r is and what theta is with respect to this axis. So when I measure theta, is with respect to the positive x-axis from there. If they want it from somewhere else, I can figure that out after. How do we find r and how do we find theta? R is the square root of r sub x squared plus r sub y squared, which equals negative 5.842 squared plus 1.165 squared. You do the math. And I get an answer 5.957. And to get theta, that's the second part of the question, it's the inverse tangent of y over x. But since we are in the second, if you're in the second or the third quadrant, the calculator will give you the wrong answer, so you have to add 180 degrees to your answer. So let's do that and see what theta is. Second tangent, negative 5.842 divided by 1.165, and add to that 180 degrees. The result is actually 178.6 degrees. They want the answer, two significant digits for R. That'll be 6.0, two significant digit. Because you got to round that up. It says my answer is wrong, but 5.95, yeah, 6.0. That's 6.0. Oh, I'm answering the wrong place. I'm putting my answer in the wrong place. Negative, negative. Just making sure. Negative, negative, negative. They're all negative. Yep. Oh, I thought it was a siren. Then you get theta after that. My mistake. I had the charge, my charge was 2.6 micro. So my numbers were off there. Notice the question for the angle says from Q2. Counterclockwise from Q, I can't read that, Q2. It says Q2 something Q3. Can you read that, what that says? Where's theta? Counterclockwise from Q2 minus Q3 direction. Is it from Q2 to Q3? I'm not sure.
Q2 minus Q3, the direction.
Q2 minus, so you gotta find out what Q2 minus Q3 direction.
When I answered mine, it was pretty close to your answer, but just different numbers. I ended up getting 174.7, and my answer was 175.
And that's,
The rounded answer, that was the right answer.
yep, so they just wanted Q2 minus Q3. I think from Q2 to Q3 means from, I think what they meant there from Q2 going to Q3 direction, which is with respect to the positive x-axis. I think that's what they meant, you know?
Because I did the same thing.
Yep.
Inverse tangent.
Yep, when you get everything, both parts right?
Yeah.
Good. Yeah, I put the wrong value there with mine, but so my question, I got the wrong answer. I was a little bit off there because it was 2.6 and I had 2.5 the charge, so it changes all the numbers. I was a hair off. Ah, go away, cough. Okay, I think we did that one in the class here, number 33, but we'll take another look at it. I did something similar to not the same one. Here's what we know. We have a ruler here, a yardstick, whatever the case is. So this is the origin, and it goes on. So at the origin here, that's a 0 mark. A charge of 9.9 microcoulomb at the origin. This is a positive charge. Positive 9.9 microcoulomb. And a negative 6 microcoulomb at 10 centimeters. So this is the 10 centimeter here. And we put a negative charge, negative, what was it? 6 microcoulomb charge. At what position X would a third charge, Q3, be
be in equilibrium. Now notice they didn't say what the sign of that charge. They didn't say at what position should a positive charge. They didn't say that. Or should a negative charge. They're just saying any charge. Well, let's think about it. Think. If I put a positive charge here between them, let's start with a positive charge here. This charge, I'm going to label that Q1 here. And I'm going to label this Q2. Q1 is going to be pushing on it, and Q2 is going to be pulling on it. So they'll never cancel each other. So equilibrium means they're going to cancel each other. You see what happens if you put a negative charge then instead of a positive charge. If I put a negative charge, Q1 is going to be pulling on it, Q2 is going to be pushing on it. Either case, they go in the same direction. They'll never cancel. If I put the charge here, let's start with a plus charge. If I put a plus charge here, what is Q1 doing to it? Pushing away. That's F1, if this is a positive charge. And what is Q2 going to do to it? Pull on it. So they could cancel each other. And what will happen if you put a negative charge instead of a positive charge here? If you put a negative charge, what is Q2 going to do to it? Push away on it. And what's Q1 going to do to it? Pull on it. So it looks like the only place that makes sense is this side. You say, what about this side here? This won't make any sense. Why? Because this charge is bigger, and you're closer to it. That force will be much, much larger. So it has to be somewhere here. Okay, let's call the distance from the charge here to this one, let's call that x. Where are we going to put it? At what position x should the third charge be placed? So I'm calling that distance x. So once we know if this is 7 centimeters, I know it should be placed at 17 because that's x centimeters away from 10. Away from 10. So I want F1 to equal F2. That's what I want to have. I want to make sure these forces are equal to each other, opposite in sign. Let's look at F1. That's K times 9.9 micro times the other charge we'll call Q. I'm going to call the charge Q I'm going to be putting there. Divided by the distance squared. What is the distance from here to there? From here to here.
19.
How'd you get 19?
10 plus 9, or 19.9. Isn't it 10 plus?
Now this is the distance, that's the charge.
Oh, okay.
Distance is 0, that's 10 centimeters, and there's going to be x from it. So 10 plus x, we'll use a meter here, 0.1 plus x, right? I'm using meters. And what is F2 going to be? K times the charge, and the charge here is what? 6 micro, times Q, the charge going to be placing there, over the distance squared, which is x squared. Here's the good news. I left it as K because it shows up on both sides. I can just cancel it out. I can cancel the the Q out. I can cancel the micro out of each one because it shows up on both sides. So I have 9.9 over 0.1 plus x squared equals 6 over x squared. Now take the square root of both sides to get rid of the square. What is the square root of 9.9? 3.146 over 0.1 plus x equals the square root of 6, 2.449 over x. And now solve it for x, cross multiply. 2.449 times 0.1 plus x equals 3.146 times x. Distribute that. Point 2449 plus 2.449x equals 3.146x. Move this one to that side. 0.2449 equals 3.146 minus 2.449, 0.697x, and x will have to be what? Point 2449 divided by that number, which is 0.351 meter. So that's 35 centimeters. So that's 35 centimeters away from 10. You're going to replace it where then? At 45.1 centimeter. So you're going to replace it at 45 because it has to be 35 centimeters away from this point. So where should we put it? 45 centimeters. That's where it should go. Oh, I got it wrong too because the first one, x was 10.5 in mine. I didn't see the 0.5 either. You know, I had a 10. I'm blind today. I give up. What's the answer? When it's 10.5? 47. Yep. So I didn't see the 0.5. So it's 47 centimeters away. It says, does the answer depends on if the charge being positive or negative? No, because I showed you both scenarios right here. It really doesn't matter if the charge is positive or negative. The same thing is going to happen there. And this is the last question, number 50 from this section. We have equilateral triangle. What does that mean, equilateral triangle?
All sides are the same.
All sides are equal, okay. So all sides are equal. Each one is 0.29 meters. A point charge of 4.9 microcoulomb is placed at each corner. Notice there's the point charge. Why the word point being used here? Because if it's not a point, if it's a sphere, you really have to worry about the radius. Where's the charge in relation to that center of it? So we have a 4.9 microcoulomb positive for each one. What is the magnitude of the electric field at the point or at the midpoint of any of the three sides? So pick one of the sides, any of the side, doesn't matter. Like this one, what is the electric field here is going to be? If it's halfway between, I like this problem. Let's call this Q1. Let's call this Q2. And let's call this Q3. Q3 is positive. The electric field for a positive charge is always pushing away. So in this case, the electric field will be pushing in this direction. We'll call it E3. For Q1 is going to be pushing away from it. The electric field is going to be in that direction. E1. And the electric field in this direction will be pushing away from it. And that'll be what? E2. Here's the good news. I can minimize a lot of the work here. Since E2 and E1, if you look at the charges are equal, they will cancel each other out. Because they have the same charge, same distance. So E1 will cancel E2. I don't have to deal with it. I only have to find the effective Q3. Which means I need to know how far Q3 from that point. What's this distance? What is that distance? I can use Pythagorean's theorem. 0.29 squared equals. This is half of 0.29. What's half 0.29? 0.145 squared plus d squared. D squared equals what? 0.29 squared minus 0.145 squared, which is 0.0631. D will be the square root of that number. 0.251. So I only have to calculate E3. If remember, E is K times Q over R squared. Just only one Q, not two Q's. 8.99 times 10 to the 9. The charge, which is 4.9 micro, divided by the distance squared, 0.251 squared. .99 e to the 9 times 4.9 e to the negative 6 divided by and I got 698,114 Coulomb or Newton per Coulomb. Newton per Coulomb. And this is two significant digits. Two significant digits, going to add 1 to this. Is that 70? Is that 70,000? Let's see, 1, 2, 3, 4. Yep. 700,000 is it? I think 700,000. And the direction is always going to be, in this case, if I look at this point, it's going to be straight down. If I look at that point, it's going to be this way. If I look at that point, it's going to be straight up. These two forces, the field for them will cancel each other out because they were the same charges, the same distance. If the charges were different, I got to find each field and do vector addition just like we did in the previous examples. But here, because it's the same charge, same distance, that means the field will be the same. And the opposite direction, that means they will cancel each other out.
finding